Today we're going to talk about the fancy name for x-intercepts. We're going to call them roots and zeros of functions. And for any nth degree polynomial, that's where you have x to a power, where the degree is the greatest power. There are always going to be n roots. Now those roots can be lots of different types. They can be real, and within that real classification they can be rational, which is what we're going to start by talking about, and they can also be complex. So, in order to find those roots, if you look at the general form for a polynomial, we've seen this before. This is your constant term down here, and this is your leading coefficient and the degree term right here. And if we want to look for a rational root, those rational roots can be found by the factors of this constant term and this leading coefficient term right here, all right, where the factors of the constant term are called p and the factors of the leading coefficient term are called q. And all the possible rational roots for the polynomial function are of the form p over q. So if I look at this, here's my p value, 6, and my q value of 1. And if I wanted to find all possible p over q values, where my p values are 1, 2, 3, and 6, and those could be positive or negative, and my q values are plus and minus 1. So my possible rational roots now these are possible. They aren't all the rational roots, obviously, because we'd have way more than 4. We'd have 8 in this case. We could have any one of these possible combinations, 1, 2, 3, and 6 of the plus and minus variety. So let's do some more examples. If I take and find the factors of this function. Now factors are a little bit different. Factors are like the zeros, except we work our way backward to find the factored form. All right, I look at the same situation over here, and I have the p values, which are the factors of 6, the q values, which are the factors of 1, and then we have p over q, which is 1, 2, 3, and 6. And unfortunately, there's no good way right now. I'm not going to tell you yet, but the way we're going to find the possible factors is by dividing each of these possible roots into this function and finding where I get a remainder of 0. And we're going to use the synthetic division method to do that. So and go, let's try a -2 and see if -2 will go into this. So I have a 1, a -1, -5, -1, and -6. And I'll take and divide that -2 into that, pull my 1 down, multiply, get a -2, -3, positive 6, positive 1, -2, -3, and what do you know, 6. Lucky guess. Not really, because I knew what the answer was going to be. However, we now know we have a root of -2. Now, I look at this and I know what's left is -3 and an x and a -3x squared and an x cubed. And sometimes you'll just luck out and get something like this. I notice right now that I have a grouping factoring situation right here, okay, where I can pull out an x squared, get x minus 3, be left with an x minus 3 here. And now, what do you know? I can pull out a common term of x minus 3, left with x squared plus 1. So, I know I have another root of positive 3, and this x minus 3 is actually a factor. Whereas I also know that x plus 2 is a factor as well, because I got a root of -2 when I solved. When you back up from a root of negative 2, we get x plus 2 equals 0, and that is my factor. Now you'll notice also we have this factor here, which is prime. However, it leads us, we said that there are going to be n factors for an nth degree polynomial. So these factors are definitely rational. I have negative 2 and 3, but then I have, and if they're rational, they're real. Then I have this term here that doesn't factor, it's prime. However, I know if I solve this, x squared plus 1 equals 0, I get x squared equals negative 1, and x equals plus or minus the square root of negative 1, which means x equals plus or minus I. So in essence, my roots for this are negative 2, 3, and plus or minus I, whereas my factors are these binomials. Moving on to this next problem. Again, what I've done for you is I've listed the possible p-values over here, the q-values here, and you'll notice this time when I use a q-value of 1, I get all these integer values, but then when I use a q-value of 2 and take the p over q value, I now get a half and 3/2, both plus and minus, as my values. So again, I'm going to just take and go ahead and make a guess. Let's try negative 3, feeling lucky. I put my 2, my 1, my negative 13, and my 6. Bring down the 2, multiply, get negative 6. And I have a negative 5, multiply, I get 15. Put a 2 down here. Oh my goodness, I gotta go to Vegas. I'm so lucky right now. And you'll notice that is going to be a root, which is negative 3. My factor is x plus 3. And you'll notice what I'm left with. I have 2x squared minus 5x plus 2. That could factor, and in fact it does. 2x, x, 2, and 1 both negative. And those are my other factors. And my roots would be a 2 and a 1/2. So as you can see, when we do this synthetic division, we end up reducing it as far as we can go until we get something we can factor. Typically that's going to be a quadratic. All right, and even if I can't factor the quadratic, I can use a quadratic formula to find the remaining roots. So we're going to again find the factors of this function. Let's go ahead and do it. We note that we've got the So we'll go ahead and find the factors of this function. Again, I've listed the p and q values for you along with the p over q rational root possibilities. I'm just going to go ahead and try a half in this case. And in so doing, I put my 2 here, my negative 1, my 10, my negative 5. Bring the 2 down. 1, 0, 0, 10, 5, 0. Once again, I have a root of a half and a factor of, in this case, if I have x equals a half, then I'm going to multiply by 2, giving me 2x equals 1, and then set it equal to 0. So 2x minus 1 would be my factor. Then I notice, in this case, I have the following. I have 2x squared plus 10 equals 0, or x squared plus 5 is equal to 0 because I divided both sides by 2. So this is actually another factor. I'll just put it over here. And essentially, I've done what the problem's asked me to do. I've found the two factors. But if I wanted to find the roots, and some of the problems you'll have tonight will ask you to find the roots, then I solve this, getting x squared equals negative 5, x equals plus or minus the square root of negative 5, or plus or minus I root 5. And that will be the other set of roots. So one thing you'll notice is that any set of complex roots I have come in conjugate pairs. Let's go back to the previous example. I get plus or minus I root 5. I think in the first example, if I'm not mistaken, I have plus or minus I. Now remember, complex roots have a real part and an imaginary part. The two examples we've done only showed the imaginary part of the root because there was no real part of the root. But this is pretty evident. Remember what I said when we used synthetic division and got ourselves down to a quadratic formula. Quadratic formulas are solved using negative v plus or minus the square root of v squared minus 4ac over 2a. And in that sense, if I get a negative under the square root, that's going to give me a complex value because I have an I. If there was a real part in the front, I would have a real answer. So know that anytime you have a complex root, you get a conjugate pair. So for instance, if I had an answer that said, well, x was 5 plus 2i, then I would know I'd also have a root of 5 minus 2i because that's the conjugate pair.
So in the case of the problem below, we've got a situation where we have two complex roots, and in this case, if I work backwards once again, so if I had x equals 3i, then my factor would be x minus 3i. Its conjugate root would be negative 3i, which means I would have another factor of x plus 3i. Likewise, for the 5i, x minus 5i, x plus 5i. And that's equal to some y value. You'll notice when I multiply these out, these are difference of squares. I get x squared minus 9i squared, but minus a 9i squared. I squared equals negative 1, so that's plus 9. And x squared plus 25 by the same reasoning equals y. Then I notice I have a situation here where it says, well, if I plug a 2 in for x, I get a 35 for y. Now clearly if I look at this example here, this gets me a 13 multiplied by a 29. No way is that 35, so something's going on. Well, what's happening is there is a coefficient multiple out in front of this whole term in order for this to actually happen. So we have to solve for that. So I have a, and that's basically going to be 4 plus 9, while this is 4 plus 25 is equal to y, which in this case is 35. So now I know I've got whatever 13 times 29 is. So that's 377a equals 35, and a equals 35 over 377. Now, fourth degree polynomial is going to be 35 over 377 times x squared plus 9, x squared plus 25 equals y. 35 over 377 times x to the fourth plus 34x squared plus 225 is equal to y. And I could distribute all these in, I'm just not going to right now. But if I ask you to write out the fourth degree polynomial I'd want that multiplied through. This next problem is a little more challenging. You'll notice we have two roots here, but one of these roots is complex, which means I need to represent its conjugate pair. So that's 2 minus I. Then I write them as factors. So that's x plus 7, x minus 2 plus I, and x minus 2 minus I. So I'm not a fan of doing a distributive property and getting 9 terms. So notice what I'm going to do. I'll keep my x plus 7. I'll distribute the negative, x minus 2 minus I, and then x minus 2 plus I. And then I'll notice that, hey, this is just addition and subtraction. I can do that from left to right. So I'll rewrite it like this, x minus 2 minus I, and x minus 2 plus I. And what I now have is really same first two, same end two, and that's like a difference of squares. So the way I see a difference of squares is the first term is squared, the middle term goes away, and the last term is squared. So therefore I have x plus 7 times, I can multiply that out pretty easily, x squared minus 4x plus 4. This ends up being plus 1. And I have x plus 7 equaling x squared minus 4x plus 5. I can now distribute all that through, which I'm going to have to do because they wanted me to find a third degree polynomial. Getting x cubed minus 4x squared plus 5x plus 7x squared minus 28x plus 35, and I'll clean that up just a little bit. I have x cubed plus 3x squared minus 23x plus 35. And unlike the last problem where I had an f of x is equal to a y, I don't have that stipulation. So this is my third degree polynomial that will satisfy it. Now, I think I've given you everything you need. However, let's just say I had a whole list of terms. I had plus or minus 2, plus or minus 5, plus or minus 5/3, plus or minus 2/3, something like that. And I had some f of x polynomial. And you're wondering, well, how's Hirsch go through and guess at, or is there an easier way? And there is. What I would do is I would put y equals into your calculator and write out the f of x. Okay, I'd also write out y equals 0. And then ask your calculator to graph. So you get some polynomial, let's say, and then you'll get y equals 0. Once you have that, you can ask your calculator to find the intersection. And these intersections, or at least one of them, should pair up, let's say it's a third degree, should pair up with one of these roots. In which case, you now know what you're dividing in your synthetic division test. Again, use that on your homework. On a test, I will likely not let you have a calculator, and the choices of factors will be less and not too difficult. So you should be able to do it non-calculator. All right? That's it for today. Until next time.